welcome to day 3 of our 3 days digital event about extending OPC UA to the field. Now we already had, I think, really interesting, informative sessions on day 1 and day 2. Before we have a look what you can expect from today's sessions, let me quickly go through the most important organizational items, mainly for those that join us today for the first time in this week. So first of all attendees are muted. This is more convenient to all the attendees as we take out any background noise and everyone is then able to fully concentrate on the presentations. The panelists also are muted only if they present. They activate audio and optionally their video. And for the Q&A, we then have all the panelists available with audio, again, optionally video, in order to go through the questions that we collect during these sessions. For submitting questions, you are using the Q&A function of GoToWebinar. So use this function in order to raise questions to the speakers, to the panelists. And these questions will then either be answered already in written during the presentations, or they will be answered during the Q&A session. Latest, they will be answered in written after the webinar when we send out a compilation of all the slide decks, linked to the recordings, as well as then this compilation of Q&A. This might take a few days after the event, but you will receive an email from us. Okay, I believe with this, yes, maybe the chat function. There's also a chat function in case of any difficulties. Please use the chat function, so we try to help you as good as we can. With that, I think we can go over to the next slides where we have a quick look on the agenda. Now, quickly going through the agenda items of day 1 and day 2. Day 1, we are starting with the overall vision of the OPC Foundation from field to cloud. We then introduced into OPC UA to the field. We heard about use cases for controller-to-controller communications, and we had first technical presentations about some of the core concepts, information modeling and connecting devices. And we had a live demonstration of C2C multi-vendor demo. Day 2, we continued with technical sessions about offline engineering and UAFX security. And we had a dedicated session on networking related topics, including Ethernet, TSN and 5G. We finished day 2 with also one live demo about UAFX over TSN, and we added one demo for OPC UA and UAFX over 5G. Now, what is the plan for today, day 3? We are starting with a first session with the focus on fail-safe communication. So we have presentations about OPC UA safety, first an overview, then we have presentation about 2 interesting development projects, Safety Stack and Safety Test Tool. We then have 2 presentations that talk about first of all, how we put together the various elements for a concrete controller profile, plus then the explanation how this controller profile can be combined with existing or future companion specifications. We hear details on the plans to do certification and conformance testing before we talk about the next steps and the outlook to the future. Okay, with that, I'd now like to introduce the first speaker. The first speaker is Christian Eitner, and he will give us what he calls a gentle introduction into OPC UA safety. Christian, the stage is yours.
Well, thank you, and welcome to this gentle introduction to OPC UA safety. My name is Christian Eitner. This is how I look like without a headset, and I work for Siemens in standardization, mainly for functional safety. And I am the chair of the OPC UA Safety Joint Working Group and also of the ProfiSafe Working Group. So let's get started. You have seen this picture in one form or the other. The challenge in modern automation is how to integrate controllers, PLCs from different vendors. And hopefully you have seen a lot of interesting presentations during the OPC days already. So we won't have to talk about what's the solution for this connection of your controllers is. The question here is, how would we integrate a safety function into a industrial network as such? And of course, the answer is we use the existent connections that are all already here between the controllers. So in short, our challenge is to implement a comprehensive safety function or several safety functions, comprehensive meaning encompassing several controllers, and we are doing that in a multi-vendor automation environment and preferably using the existing communication infrastructure. So we do that, and if by now we are of the opinion that OPC UA is a good idea covering our communication infrastructure in the field, then OPC UA safety is the solution on top to implement functional safety. So that is what OPC UA safety is. It extends OPC UA for safe data exchange in an application independent way, and the goal is to detect communication errors. So what does that mean? Extending OPC UA. That means we have at the bottom here an existing communication implemented via OPC UA. So in the context of UAFX, that will be pub/sub. Could also be client-server communication. And on the top level here, we have the logical view. We have safety applications that want to communicate, and we want to make this logical safety application communication possible. Doing this, we will introduce a concept. So we will have one part that has data that is of interest. We call that the safety provider. That's on the left here. And the safety consumer that is interested in using that data. And so we will have a concept of the safety consumer sending a request to the safety provider and the provider answering with the data. And if we map this concept to our safety application, we can have the logical communication on the application layer that we wanted. To do that, we have to have a small layer that connects this conceptual layer of safety provider and safety consumer to the existing OPC UA communication, and this is called the OPC UA mapper. this is mainly how the data is provided to the protocol. And what we see here is a schematic diagram. So the safety provider, this is actually the true state diagram. So the safety provider is a very simple state machine, basically waiting for a request from the safety consumer and answering it. On the other side, the safety consumer is a little bit more intricate and complicated. So all the logic about failure states is implemented on the consumer. The big advantage is that the provider can be kept very simple and small and is therefore very scalable. So in our graphic here, we see 3 layers now that we have talked about. So at the bottom, we have the existing OPC UA communication, the OPC UA layer. At the top, we have the logical application layer, the safety applications that want to talk to each other, implementing safety functions. And in the middle, we have this concept of safety provider and safety consumer, making the safe data exchange possible. And that is OPC UA safety. What we also see is a color scheme hinting at how these layers and parts of layers shall be implemented. So yellow here means that you need a safety related implementation to make sure that the things work correctly according to the norms and regulations for fail-safe communication. And parts that are not in yellow, grayish black here, can be implemented in a non-safety related way. Of course, they can be implemented in a safety related way too. Yeah, and congratulations. By now you have hopefully gained a little understanding. This is the first diagram you will encounter in the OPC UA safety specification, because that's how you should read specifications in the first run, skimming over the diagrams and tables. And hopefully you have understood this first diagram now. When we look at the safety application layer on top, this logical layer, so we haven't said anything about what this application actually does, which kind of data it exchanges. This can be done in companion specifications. There is a well-established process for that in the OPC Foundation, and for specific application domains, companion specifications can then be specified. So what we will do now is we will have a little deep dive look into how OPC UA safety actually works and provides the fail-safe communication mechanisms. So there is an international standard that covers how functional safety field buses, so how communication in the field level for functional safe communication shall be implemented. And the main methodological thing here is the so-called black channel approach. This means that there are no requirements regarding the underlying communication mechanisms. So the safety protocol that is implemented on top will take care of detecting all kinds of communication errors without knowing how the black channel, underlying communication channel, actually works. And yes, this is done via an error model. So this international norm specifies all kinds of possible errors that can occur in the data transmission in the black channel. The classical things are a bit or several bits get corrupted, a message is repeated, or messages are sent in the wrong sequence, or messages are lost, things like that. And all of these things from the error model have to be covered by the fail-safe communication protocol. So OPC UA safety gives you the possibility to have logical connections in a unidirectional, bidirectional, or multicast way. So what does that mean? If we have one safety application sending data to another one, that's a unidirectional logical view on how the data is flowing. If both applications communicate, that's bidirectional. And if one application sends its data to several others, that's a multicast scenario. Also important, and even more important in the future, ever more, is the concept of dynamic connection establishment. So you want to start and stop those OPC UA safety communications dynamically. There is a wide range of how the application data size can be structured, so from 1 to 1500 bytes. And as we have already seen with the black channel approach, also the arbitrary network topology is possible, so there are no requirements regarding how your network looks like. OPC UA safety uses well-established mechanisms to make sure that all the errors that we saw in the error model can be handled. So CRC checksums or so-called seal monitor. I will only gloss over these terms right now. But also more importantly, there are no requirements to the non-safety components making up the black channel underlying communication. The number of network components is not limited, and the packet rate isn't either. And a very important concept is that for OPC UA safety, you don't need to safely synchronize clocks across the network, which greatly simplifies the implementation of the protocol. This is also the reason why we saw this request response scheme. So the consumer is always requesting something from the provider. This makes possible that the consumer is doing all timing checks on its side without having to synchronize clocks with the safety provider. All of the mechanisms I've shown you have not been invented anew for OPC UA safety, because that's usually a bad idea when working in functional safety. So these concepts come from an implementation that has already been in place. So it is one of the profiles for the international norm I've been showing you. And I'm not reading out this number to you. It's very complicated, but you may know the protocol under its name ProfiSafe. This is also the reason why the OPC safety working group is a joint working group between the P&O or PI, where the ProfiSafe protocol is hosted, and the OPC Foundation. So what is the roadmap for the standard? We have already had 2 specifications that have been published. So the numbering scheme is from OPC Foundation. Our first one, it was release 1.04, covering client-server communication. And last year was 1.05, covering pub-sub communication. The integration with UAFX is indistinguishable between pub-sub, pure pub-sub, and UAFX on the runtime. So we are covered for UAFX here already. These specifications talk about the controller-to-controller scenario. A controller, we have made a simplification. A controller is a thing that is completely parameterized by vendor-specific tools. This, of course, greatly simplifies the specification. And as I already said, the way that the pub-sub information model is used to transfer information is the same mechanism that is also used in UAFX. So UAFX is already covered by these specifications. Currently in development are a test specification and a test tool, which is important for certification for your functional safety devices. And on top of that, there is now in member review a version that deals with error corrections. Of course, if you test, then you find errors, and we corrected those. Also, being implemented right now is a stack implementation that is available to OPC FLC initiative members. So if you're interested in that, contact Peter Lutz about it. And in the future, we will have a specification covering controller to device. I already mentioned a controller is currently defined as being something that is completely parameterized by vendor-specific tools. And you can imagine if you want to deal with lots of devices and a controller in the field, you don't want to parameterize each and every device in a vendor-specific way. So parameterization will be a big topic in that new specification stage. Okay, to sum up, OPC UA safety gives you application-independent safe communication, and using proven safety mechanisms result in a simple design. We have dynamic multi-directional communication patterns, and the black channel approach doesn't give us any requirements on non-safety components. The design of the protocol is for controller-to-controller communication and the field level. Yeah, that was my part, and I'm interested in your questions later in the Q&A. Thank you.
Thank you, Christian, for the introduction to OPC UA safety. I think this is very useful also to better understand the two following presentations that deal with two development projects. We start with the development project of safety stack. And as you already mentioned that shortly in your presentation, Christian, I'd like just to add one comment. So the access to this safety stack is not limited to the FLC steering committee members or the FLC working group members. Actually, all the OPC Foundation members can sign up for this joint development project and can become co-funder. And with that, they have early access to the developed software as well as to the documentation that is being created for this stack software. Now, this is the perfect intro or transition now to Elke Hintze from ifak in Magdeburg. Elke will now explain to us the details around this joint development project of a safety stack. Elke, please go ahead.
I'm the project leader for the OPC UA safety stack development project, and I will introduce you now in this development project. So I will tell you some overall information, which the topics of the requirements to the stack development, the architecture of the UA safety stack itself and its interfaces, but also to the reference implementation that demonstrates the integration and the use of the stack, some facts to the implementation of the so-called OPC UA mapper, then to the expected project results, and at the end, something about the co-funding of the project and the planned license concept. The protocol-specific and certification requirements are implementation of the OPC UA safety profile version 1.05 that actually is in the final review. We have the two roles of the safety provider and the safety consumer, and all protocol-specific requirements are marked with unique identifiers in the specification. So that is a good position for our requirements tracking in the project. The stack will be developed according to the relevant safety standards for software, for safety standards in machinery, factory and process automation as a prerequisite for later safety product developments. And the stack will be pre-certified by a notified body. In our case, it is a TÜV Süd. Then here is a selection of the main implementation requirements. We will implement the stack in the ANSI C99 standard and fulfill the coding guidelines of the MISRA C standard. The stack itself will not use library functions, but the reference implementation, but we will use only C standard library functions for the implementation. The implementation will be independent of any target processors, byte orders, compilers, operating systems, and also of the design. For instance, if you later on want to use a single channel design, that is possible up to safety integrity level 2 or 2 or more channel designs. In the case of 2 or more channel designs, you have to know the synchronization between the channels will be outside of the stack. The advantage is that the integrator has full control about integration. Source code documentation can be generated via Doxygen, but besides that, of course, we have the full document package that is necessary for safety development. So this is the overview over the stack architecture. We have several interfaces: the safety application programming interface, the safety parameterization interface, and a diagnostic interface related to the specified interfaces in our standard. And additionally, we have a safety instance management interface to set up and execute the instances. Core of the stack are the safety provider and safety consumer implementation, and you can configure as many instances if you need, and resources on your target platforms are available. The interfaces are of two types. The instance management is a function interface, and the application and parameterization interfaces are data interface based. On the lower interface of the stack, the request and response safety protocol data units will be exchanged, and here we have data interfaces. A little bit more in detail on this picture. The safety management interface contains functions to initialization, parameterization, start, execution, stop, and reset of safety provider and safety consumer instances. All these functions beside some initialization parts are instance related. So the integrator has full control of the program flow. If, for instance, the execution of all functions will be in one main loop, or if he wants to implement later on tasks for the several instances. Then, and as I told, we have a data interface to exchange the protocol data units at the lower interface to the communication part of the OPC UA stack, and also for the process values, the safety inputs and outputs. The initialization of this data interface will be done by the integrator and the startup with the initialization function, and later on there are measures to inspect that no unallowed change, access or something can happen on these data interfaces. So then, yeah, we have then the implementation modules for the CSC calculation and for the necessary timer instances at the safety consumer side. Oops. The safety stack will be integrated in the implementation of a safety device. We call it reference implementation. The reference implementation itself is not safety related and will not be certified itself by the TÜV. But of course, we need this reference implementation in the verification and validation of our stack to, for instance, to reach the necessary test coverage, but also to demonstrate the integration and use of the stack to the customers. It is based on a system with at least 10 safety provider and 10 safety consumer instances. These numbers is related to the embedded platform we use. On a PC platform, of course, we will execute it also with larger number of instances. We use a 1 out of 2 safety architecture with certain ARM processors. We use no operating system, no multi-threading system, and the OPC UA communication is based on the Open 62541 stack. For the reference implementation, we have to implement the example of the so-called OPC UA mappers, and we do it for client server and also for PubSub via UDP. The reference implementation has to pass the OPC UA safety conformance test. And as I mentioned, it will not be certified itself. And here we have an overview of the variant with the safety platform. We have 2 channels on the safety platform where the OPC UA stack is integrated, and we need several test applications during conformance or our system test. We have a module for test configuration and main loop for the execution. And of course, we need synchronization interfaces. On the one hand, to the communication part that is running on a PC platform. And on the other hand, between the both safety channels. So there will be also variants where all parts are running on a PC. That is the very first beginning for vendors to find out how to use the stack. The stack is hosted on a GitHub project of the OPC Foundation, and if someone downloads it, it can directly build the PC variant of the stack and can run it with example configurations. Here is a selection of the interface of the OPC UA mapper. We have an exemplary configuration interface where several configurations with different instances, parameter types, and so on can be set up via a configuration file. Then the instances can be started and stopped separately. And then for the different mapper types, we have separate interfaces. Here is a selection for the safety provider mapper and the safety consumer mapper. The interface is independent of if we use, for instance, client server or PubSub. Yeah, for the test, we need further mapper types, but I will tell you in the next contribution about the test. And here is an example of the implementation here for the safety consumer mapper based on client server. The consumer uses the client role. Yeah. So safety stack can set and get the request and the response SPDUs inside of the mapper. The latest version of the SPDU is cached, and then the mapper executes the communication function, in that case calls read safety data services, and the mapper is responsible for handling retries in case of errors or receiving old response SPDUs and so on. So the project results, we will have at the end the pre-certified OPC UA safety stack that includes the source code documentation, a safety manual, an integration guideline, and the integration guideline will include integration rules for the developer of safety devices that has to be fulfilled. Then we will get the non-safety reference implementation, also source code documentation, project files, configuration files, and so on. Then we will have the complete BNV documentation packet. This, for instance, requirement specification, safety plan, design and test specification, and the results, all the results of unit, system, performance, and conformance test. And based on this documentation package, we will do the assessment at the TÜV Süd, and at the end, the reports of the pre-certification will also be available. The projects, both safety stack and safety test tool development, are funded by a group of companies from the field level committee. Part of these group members are working in a so-called advisory group, where we have cyclically meetings where we discuss the requirements and present the the status of the project and the results. The coordination has been done by OPC Foundation. OPC Foundation contracted us, ifak, Institut für Automation und Kommunikation, as a service provider for the stack development, and also the TÜV Süd as a notified body for the assessment of the stack. And at the end of the project, 2 types of licenses are planned. The one type for product developments is a commercial license. It will include all the results of the project. That means the source code, the full V&V documentation, and also frequently updates and so on. But there is a second type of license planned, the open source license, with one version of the source code and basic documentation that can be used for evaluating the stack in projects in own environments. So that was my overview about the stack project. And yes, I'm waiting for your questions later on.
Thank you, Elke, for the insights to the safety stack development. If you are interested in further information and probably want to become a co-founder, just contact me and I can provide further information. Now, in the following, it's again Elke's turn. So Elke is in the following presenting the OPC UA safety test tool, which is currently also under development, which we will use to enable manufacturers to do pre-testing of their safety implementations, but certainly also using the tool then for the certification of safety devices. So Elke, again, over to you.
I will tell you now about the OPC UA safety compliance test tool. I'm not internally the project leader of this project, but responsible in the OPC UA safety group to discuss the concepts and present the results. I will give you an overview of the project because it's a safety related test tool. It's more than only the tool development. Parts are model simulation, model-based test generation, then some main test tool features, test tool concept, and the requirements to the systems under test. They have to implement a so-called upper tester application as a precondition for testing. I have a short address-based example of such a system under test, and then a short demo of test execution prepared. To reach the necessary coverage and requirements to a safety test tool, the project started with modeling of the behavior of the OPC UA safety protocol. We did the UML model in Rhapsody tool as a basis for all the other test steps. First, some model checking steps have been done. Then the model was imported into a simulation environment. In the simulation environment, in the early stage of the specification, we simulated the behavior of the state machines. made some improvements. And now in the later stage of the project, we can use the simulation as a test partner, for instance, simulate the one role in the simulation system against an early prototypes, proof of concept implementations. And then a second variant of the model will be imported in a test case generator, where test cases and from that test scripts were generated with a sufficient test coverage. And the last part is then the test tool development that executes the test scripts so that implementations can be tested for conformance with the protocol. This is a short snapshot of the simulation. Inside of the simulation, we can animate the state machine. One main feature is that all the model elements are presented in an observe view, where we can observe all the model elements and also manipulate. So it was possible to simulate a lot of use cases and found out in the early stage of the specification improvements of that. Later on, here you see that a snapshot of a simulation of the consumer role. The partner is our prototype, PC-based prototype of the stacked implementation as a server role. And so we can do plug test with the simulation too and use it as a test component. Then we have a tool chain for the model-based test generation. I will not explain it today. With some special features, for instance, the meta editor that allows us to separate test suites, for instance, for optional parameters that are the dynamic IDs. That's the safety application interface. So we have test suites without using these IDs that have to be will be mandatory for all implementations, and we have additional test suites with using of this dynamic IDs that will be mandatory for devices that support this behavior. The main features of the test tool development: it will be a T2 tool according to the safety standard 61508 and also assessed by the TÜV Süd. It will be a Windows tool with a graphical user interface to set up the test projects, to select and execute test cases, display the results and test events, generate report, and so on. But we will provide also a command line interface. So projects that you set up with the graphical user interface, you can later run from the command line interface. And so it can be integrated in test campaigns and so on. Then one main requirement was to have separated binaries for the test tool part and for the communication part. So the test tool part is the safety related part and under assessment, but the communication part, the OPC UA stack plus the necessary mappers are the non-safety part and not under assessment. So we will be able to make improvements in this part without recertification of the test tool. And communication is also based on the Open 62541 stack. The configuration shall be done by browsing the address space of the system under test. So that is very easy to set up a project. And if you later on want to follow here the slides, there are some terms and abbreviations, but I will not explain it in detail now here. So the test concept is, on the left side, we have our system under test, an OPC UA safety device, for instance. And inside of this device, there is our implementation under test, our OPC UA safety instances. And to test the behavior, we need to test on both interfaces, on the lower interface and on the upper interface. The lower interface we can stimulate indirectly via the safety SPDUs, the normal OPC UA safety conformance channel. For stimulating and observing the upper interface, we need an additional test control channel. That is here with the blue line. And this test control channel is similar to the OPC UA safety connection, with the difference that we transport the parameters of the safety application interface. The specification of this channel and of the so-called upper tester application is included in a test lab specification that we provide from the working group 2. The upper tester application is also responsible to copy the parameters for the application interface to the test control channel and vice versa. And here on the left side, you see the test tool. Parts of the test tool are the so-called lower tester. The lower tester stimulates the lower interface of our implementation under test and observes the behavior, the outputs, and the upper tester does it for the upper interface. The test tool parses the generated test scripts and then builds the commands on these both interfaces, executes the test steps, and then produces a test report. Yeah, the main commands in the test scripts are setting and getting SPDUs, setting and getting the parameters at the safety application interface, that is both for safety provider and safety consumer test. For the safety consumer test, we have additional test steps to generate a consumer timeout. In this test step, the test tool will not send SPDUs for the configured timeout interval, and after that, so the expected reaction is that in the system under test, the timer has been expired, and the test tool can then check with the next test steps the reaction, receiving failsafe values. The second is the test of the error interval timeout. Error interval timeout means error-free communication. So for the configured time, the test tool communicates with the system under test, and after the timer has been expired, the next test steps can then check if single errors will be ignored by the system under test. So then I come to the requirements to the system under test. As I mentioned, it has to implement the test control channel for the test, the so-called upper tester application, to copy the input and output parameters of the safety application interface to a second communication channel. We use a client server for this test control channel, and on the device under test, both the safety provider upper tester and the safety consumer upper tester uses a server role, and for that, two services are specified: the get safety data, the get test control data service and the set test control data service. All are specified in the test specification. And here is a short overview about the upper tester application. It is also responsible to copy the parameters for the application programming interface to this test channel, and then OPC UA service is used to transport it to and from the test tool. We see here a short snapshot of one configuration example in the address space for the safety, OPC UA safety instances. In this example, we have two instances, a safety provider 1, a safety provider 2. The safety provider offers the read safety data service as specified in our protocol, and we have all the parameters. The test tool will browse the parameters and will use the read safety data service from the by the upper tester. And for the test control channel, we have a similar structure for each instance that shall be tested. We need an instance of the upper tester application, and this instance contains additional parameters, for instance, the data values that shall be used during the test, and it has to provide the read test data service and the write test data service. So, and now I prepared a short recording of test execution. In that case, the system under test has 7 instances, 5 safety consumer instances, 2 safety provider instances. To set up a test project, we only need the URL of the system under test. Then we have to start our system under test. That is here the PC variant of our stack implementation. And then we start browsing the information model of the system under test. It takes some moments. It browses the address space of the system under test and tries to find matching pairs of safety provider and safety provider upper tester application, or safety consumer upper tester application. It presents the testable instances, and you can choose or not, and then set up the test project. We need a project name. And then the test project will be generated. It will be presented in here, the project window of the test tool. For each instance, the test cases are presented. And then the project is ready to start. You see here, dependent on the instance type and the parameterization, the different test suites will be used. We can start now the test. And in the log window, all the test events can be observed. You will later on, if developers have to deal with errors, will find for each test step the parameters of the SPDUs and test data that are sent from the test tool to the device, and the received parameters and SPDUs, as well as the expected parameters and SPDUs. In this short recording, there are no errors included. Yeah, I stopped here the test. The actual version has also the possibility now to run until the first error or run the whole test suite. On the left side, after finishing the test, you will get here the short information about which test cases are not executed or have passed or the test or failed. And on the left side, you can change to the report view, and it was shown that the report can be printed, for instance, in a PDF file. And then, of course, during in-house tests, you can choose only single test cases, as I do here, and execute then only the selected test cases. Once you pre-configured via this graphical user interface, sorry, and the project, you can run the project also, the test project also from the command line. Okay, maybe we can skip a little bit. Here, for instance, you see the error interval timeout test step. That means for the configured error interval time, the test tool has to do normal error-free communication. Maybe that is a consumer timeout, so the test tool will not send SPDUs for some time. Yeah. And at the end, as soon as the test has been finished, the status bar will change the color to green if the all tests are passed, or to red if at least one test has failed. And then again, you can inspect the test report, and you can print the test report, e.g. to a PDF file. The test report itself is in an XML format, so it can be used in further tool chains in overall test campaigns. So from my side, I would at the end and wait for your questions in our
Thank you, Elke, for your interesting presentation and for giving us explanations about how the testing of OPC UA safety devices works or will work in practice. A quick reminder, please post questions that are interesting for you to the GoToWebinar using the Q&A function, so that our experts are then able to answer them for you. All right, we go now further in the agenda and start with our next session. For this, I would like to quickly introduce the content of the next two presentations. In the first presentation, Schreck, Majcher, will explain to us the concept of so-called UAFX profiles. This is the content of part 84, and this deals with the question, or let's say the guidance, what elements are being combined for a concrete UAFX controller implementation. And then we have, following the presentation by Paul Hunkar, who explains to us how the different companion models or companion specifications, how we name them, are being combined or can be combined with this UAFX profiles. With that, I'd like to hand over to you, Greg. Greg, the stage is yours.
Hi, everyone. My name is Greg Majcher from Rockwell Automation, and I am the chairman of the technical working group for the FLC initiative. I'm going to talk to you today about UAFX profiles. I'll start by giving you a little background in OPC UA conformance, and then I'll talk specifically about what we've done to create one controller profile for the controller to controller phase of UAFX. And then finally, I'll wrap up by giving you a little demo of OPC's profile reporting tool, where all of the conformance information is stored. So let's get started. OPC UA profiles report testable OPC UA functionality. The smallest thing that you can test is referred to as a conformance unit. Multiple conformance units can be grouped together to form what's called a facet. Facets can be used to represent features of a product. And then profiles are collections of individual conformance units, facets, and even other profiles to put together all the functionality that's represented in an application. It's worth noting that multiple profiles can be supported at one time, and that facets and profiles can contain optional information. Let me show you a few quick examples. As of version 1.05 of OPC UA, the specifications now include an indication of what the conformance unit is to test object types. So if you look into a specification at the very bottom of the table that documents the object type, you'll see an indication of the conformance unit. Here's an example from the UAFX specifications where our FX asset type is tested using the UAFX asset-based conformance unit. I'll point out to you while we're on this slide that there's a lot of optional information in object types, and on the next slide I'll show you how that's handled. The conformance unit that's indicated at the bottom of the type definition table indicates that you support the type. But as I indicated on the last slide, many types have optional pieces of information, whether it be a method or a property. In order to indicate support for those optional pieces, we specify individual conformance units. In this table, I have two of the properties that were shown, optional properties that were shown in that table. The component name from the iTag nameplate interface and the device health diagnostics alarm from the iDevice health interface. Both of those are optional in the FX asset type. And so for a device to indicate whether it supports these or not, we write a conformance unit that can be included in that device's conformance profile. Individual conformance units can then be grouped to form as a collection to form a facet. An example of this might be all the functionality needed to push security keys to servers that are on a network. Here I have the security key server facet where all those conformance units are bundled together to form the SKS facet. You can see that some are required and some are optional. And finally, as an example of a profile, and we will see one in a minute for the UAFX controller, profiles can include a server, a client, facets for features like an SKS, and then individual functionality defined by CUs. When we started the FLC initiative, we established some requirements for the UAFX profiles. Obviously, conformance testing is in place to guarantee interoperability between devices, and we certainly need to provide for that. But with many vendors coming from different backgrounds and having different business models, we also wanted to balance interoperability with optionality for vendors in order to achieve the broadest range of adoption in the end. So we only specified what was essential for interoperability, and we left a lot of options in the profile to guarantee that broad range of adoption. We also wanted to write the profiles and facets in such a way that when a device is certified, an end user can look at the conformance certification and know what's in that product. It will make it much easier for them to select products from multiple vendors that are guaranteed to work together. We were also asked to spend a lot of time thinking about reuse. We invested a lot of effort into building these profiles, and in this first phase of the FLC initiative, it was for a controller-to-controller operation. But we know in the near future, when we move to controller-to-device operation, that we want to be able to reuse as much of this conformance information as possible. So there was an emphasis placed on writing the facets in a way that we could reuse them on devices. And finally, for the C2C phase of the initiative, we were asked to try to write one profile. We didn't want to have users pick from multiple profiles and then be confused about whether those devices would interoperate. And I'm pleased to report that we satisfied all of these objectives in our definition of the profile. UAFX has 5 specification parts. Part 80 provides a high-level overview of the architecture. Part 81 describes connecting devices and provides the information model for that. Part 82 includes all of the networking-related aspects of UAFX, and Part 83 describes our offline descriptor and the operation of engineering tools. Part 84 is the document where all of the conformance information is contained to cover the normative aspects of parts 81 through 83. To help manage the information across hundreds of pages of specifications, conformance units can be organized into groups. We have approximately 200 conformance units for UAFX, and we've organized them into conformance groups that follow the architecture as defined in parts 81 through 83. There's the automation component, which is effectively the core of every UAFX device. There's the FX asset, which is the asset model representation of products in UAFX. The functional entity models functionality in a device that supports UAFX. The connection manager is the collection of features that allow a device to establish connections between two servers. Networking is where we describe all the aspects related to how the device attaches to a network. And offline engineering security cover the operation of engineering tools and of our offline descriptor. This is a very high-level overview of the UAFX controller profile. Every controller will have the elements that are listed in this upper box. Every controller has a server. They all have our core automation component facet. They all have an asset facet. They all have a top-level functional entity facet. And it says top level because there's an opportunity for nesting of functionality. So there can be sub-functional entities below the top-level functional entity. And then there's the publishing and subscribing facets. The publisher and subscriber profiles specify how we will apply PubSub and UAFX. They rely on UDP as a transport protocol and UADP as a message mapping. Data has a fixed layout and it's exchanged periodically. All of that is described in the UDP, UADP periodic fixed profiles for both publishers and subscribers. All controllers are required to have a connection manager. The connection manager is what allows a controller to establish connections with a partner. So by requiring all controllers to have a connection manager, this guarantees that end users will never have a system where they bought two controllers that can't establish a connection. Every controller will be able to establish its own connections if need be. And finally, there's a UAFX station facet, which describes everything required related to the networking aspects of the controller. At the very bottom here, you see a safety facet. The safety facet is defined by UAFX. It's not included in the controller profile because controllers can be shipped with or without safety. This facet is defined and it can be included in a controller if safety is supported. So now I'll go into some details on some of the individual facets that were in that high-level overview. This is the controller server profile. And as you can see, we started with the Nano Embedded Device 2022 server profile. This is a very small profile, and the reason we started there is, again, because we had an objective to provide for very broad adoption. So we want to ensure that vendors can implement our profile from the smallest controllers to the biggest, most powerful controllers. So we started with the embedded, with the Nano embedded, and then we added everything that was needed in order to meet all of the requirements that were given to us for UAFX, such as event subscriptions. Event subscriptions allow the controller to subscribe to events from other controllers. Auditing requires the controller to log events when a client performs certain actions that change the state of the server. Those events can then be used to create an audit trail. Time synchronization for this release, for controller-to-controller release, is primarily to guarantee that we can track the expiration of a certificate. Further time synchronization needs will be introduced in our C to D phase. And the remainder of the facets that you see in this profile are all related to the security requirements that we had for UAFX. This is the UAFX asset facet. As you can see, it is heavily based on the information that's described in the DI spec, Part 100. We use the iTag nameplate, iDevice Health, and iVendor nameplate interfaces from Part 100. The one thing that we changed from Part 100 is UAFX wanted numerical revisions to provide for easy verification. And so we defined our own revision that includes numeric values for major rev, minor rev, and sub-build revision. In addition to what's in the asset facet, there are also facets that describe the physical connection of a device to a system. Many industrial automation products are in modular systems, backplanes. And so these facets describe the physical connection that an asset can have to the system. The connection manager facet requires client behavior in the controller. So we have specified the minimum UA 2022 client profile, and also the user token X509 certificate client facet is what allows the controller to use X509 certificates to identify connection partners. Additionally, we have the SKS push facet, which, as I described before, encapsulates all the behavior needed for a controller to be able to push security keys to devices on the network. And finally, there's the subscriber configuration facet, and that includes all the information needed that the subscriber end of a connection needs at the very end of the configuration process. It's things like the network address for the subscriber and a message received timeout. This is a model of the networking facets. I'll go from the inside out. The end station facet describes the functionality needed for sending and receiving network traffic, including the use of tagged Ethernet frames. That facet is included in the IA station facet, IA standing for Industrial Automation. An Industrial Automation station describes the functionality needed by industrial automation products such as topology discovery, remote management, and time synchronization. It also provides the ability to include optional bridge behavior. Products that have bridge behavior can include one of 3 defined bridge facets that specify bridge behavior starting from a basic bridge all the way up to a full-featured bridge that includes things like per-stream filtering, frame preemption, and gate control lists. At the very top of this hierarchy is the UAFX station facet, and that includes things from OPC UA's base network model, such as priority mapping tables. The UAFX controller safety facet simply groups together facets that were already defined in OPC UA's Part 14 to model a safety device that is both a safety provider and a safety consumer using pub/sub. Finally, we have defined a tools profile to provide guidance to vendors on what functionality their engineering tools will need to have in order to participate in a UAFX ecosystem. UAFX defines an offline descriptor that's used to exchange information between those engineering tools. The engineering tools need to be able to import and export descriptors using the security policy specified in Part 83. And that's what's shown in these import and export profiles. Part 84 is a document that describes all of the conformance information for UAFX. It's analogous to OPC UA's Part 7, where the conformance information for all of the core specifications is defined. However, the tests are driven by the information contained in the OPC Foundation's profile reporting application. I have the URL here on this slide. If you want to go and visit this site, you can see the tool for yourself. We have already started importing the information for Part 84 into the tool. It's all currently in draft state and will remain in draft state until the Part 84 is released. But once it's released, this profile reporting application will be the source of all of the conformance information for UAFX profiles. And now I'd like to give you a demonstration of OPC's profile reporting application. When you first enter the tool, this is probably what your screen is going to look like. I'm going to show you how to change that view. You can select profiles or conformance units here. You can choose to look at either the released, release candidate, or even draft information in the tool. And you can change which part of the database that you'd like to look at by changing the group here. So first, let's take a look at profiles that are release profiles in the core specification. As you can see, these are the profiles organized by category in the core specifications. I'm going to switch to draft and release candidates. And let's go and look at the nano embedded device server profile that we're including in the UAFX controller. So you can see that it shows you the individual conformance units that are included in the profile, and there's an indication as to whether that conformant unit is optional or mandatory. The conformance units are sorted by their conformance group in this list. And then it also shows you included facets and profiles that are in this nano embedded server profile. And finally, down on the bottom, you can see if this profile is included in other profiles. The micro embedded device server profile includes the nano embedded device server profile. So that's a top-down way of using the tool. So now let's try a bottom-up way. We'll go and select conformance units, and we're looking at released conformance units in the core specifications. And now those conformance units you can see are organized by conformance group. We can search for something from all of those. So let's search for SKS conformance units. And you can see I've now filtered the list for only things related to SKS. So let's now go take a look at the UAFX conformance information that's been entered. So I'll change the working group to UAFX, and I'm going to select draft only because we only have things in the draft state. And I'm going to choose profiles. And let's go take a look at how the UAFX controller profile is represented here in the tool. Okay, so you can see all of the individual conformance units over and above the facets that are included. And here are the included facets. You may recognize them from the figure that I showed of the overview. There's the automation component, the server, connection manager, UAFX station, asset facet. And that gives you a basic overview of how to use the tool and how to navigate between conformance units and profiles. I hope I was able to give you a better understanding of OPC UA conformance, and more specifically, I hope you have a good understanding of what we've done to build a controller profile for the FLC initiative. My contact information is listed here if you have any questions, and thank you for your attention.
I'm Paul Hunkar. I'm talking to you today about companion specs. I spoke on day one about information modeling, and we're going to talk a little bit about companion specs and how you can apply FX to existing companion specs and how that would work. With that, let's get started. Oh, by the way, I'm a consultant working for Yokogawa. I've been involved in OPC for a very long time. I'm also director of certification for the foundation, so I have 2 jobs as a consultant. Anyhow, let's get on and talk about companion specs. All right, let's start a little bit about what a companion spec is. The foundation defines a core set of specifications, but we know that we're not experts in every possible field And so we allow and encourage actually companion specs to be written that are written by experts in specific topics, right? There's over 60 working groups right now. They have over 35 released companion specifications already. They include pretty much anything you could think of at this point already. There are vertical market companion specs for specific lines of products, like oil and gas industry. There's also specific equipment type models like woodworking equipment or commercial kitchen equipment. There's also mapping to other standards like ISA 95 or PLC Open. So there's a wide range of companion standards out there. Some of them apply to FX a little bit more than others, but the key thing is there's a pretty large list of companion standards available. If you're interested, they're available on the foundation, both the list of collaborations and markets that we're working with, and then also you can actually see all the released companion specifications. So let's talk a little bit about FX and how it can be mapped to a companion spec, right? So if you were present on my day one, I talked about the information model, about, as Greg mentioned just before too, that we have an automation component, we have assets, and we have functional entities, right? So if you have we're going to talk about how different types of companion specs can map things. So if you're writing a brand new one, we'll offer some suggestions, and your new one wants to include FX, how you could do that. We'll also talk about existing companion standards that have already released specifications, and they want to release a new version that includes UAFX. Some of these may include some of the device integration pieces that Greg mentioned. We based a lot of our asset models on. And if you didn't include any DI in that existing information model. We'll also talk about companion specifications that cannot be updated, but they want to create a standard mapping. So that, it's not that we're going to change the existing specification, but we want to have a standard way of mapping it into UA. And lastly, if you're an OEM or an end user and you want to apply UAFX and you already have existing information models running, you can do that too. We'll explain how you can load an FX system in parallel effectively. So let's go through that a little bit. I put these slides in there from the information model one, but just to refresh your memories a little bit. We have an asset model that's based on interfaces. It has the vendor nameplate, the tag nameplate, the device health, and the asset revision one. And then we have a functional entity interface, which also, or a functional entity model that also has an interface associated with it. So the entire contents is also available via an interface. So let's go through a little bit. And I think to explain how to do this, it's best if we just look at some models, some instances, and some somewhat fictitious sometimes, but illustrations of how you could do different things. So if I have a new model that I'm building, I can define the model such that it's actually based on the FX asset type and the functional entity type. It has filled in, maybe I created a subtype of it that adds mandatory subfunctional entity or mandatory methods or other mandatory pieces for it, right? I can add a specific set of assets that I want or specific structure. And the key thing is I also add an automation component piece that links it all together. So if I'm building a new spec, and this is jumping around on time, I can pretty much build the model how I want, create a subtype of things, and apply it. So this is a typical way that I may want to do it for a companion spec, like the motion group that's working on things may very well do this. So they're going to create subtypes of functional entities and build it around FX. I could also build it with much more defined, right? So I could build a model that actually includes input data, output data, so it's a fixed data model. This is something that we'll probably see when we get into the device world, where we're defining a temperature sensor or some other smaller device. They may very well have a fixed set of input, fixed set of output, so the model's very fixed. So these are sort of the easy ways, because we're just going to use the FX-based model that we build and build something with it. So let's talk a little bit about updating existing models. So if I have a companion spec model that has some data in it, it maybe has some commands that it does, maybe it has some status information even. And by the way, it used the iVendor nameplate for some information about the model. Notice it doesn't differentiate between functionality and assets, it just has a model, right? So I can add a UAFX information model to it. I have a functional entity that organizes the data that I want to report. I added the other DI interfaces that we would require so that I have, sorry, my screens are jumping. I added the DI interfaces that are allowed for or required for the asset model. And the key thing here is that I layered this in. I didn't have to make changes to their existing model. I made a bunch of additions. And I did it by adding interfaces into the existing model. I did create a new instance. I need an automation component type. That's part of what I create. But it references the existing instance that they had of their model, right? So this gives me a way of utilizing it in a model that exists with DI. I did update the model so that it has UAFX in it. But if that's the desire, this is one way you could do it, right? So I can also have a model that maybe I don't want to update the instance, right? Or the type rather, but I want to just deploy it in the instances. So I can create as part of my spec, define how you'd apply the interfaces. Mind you, interfaces can be applied to types and to instances. So I could take my model instance, add the interfaces into it. Yes, I still need an automation component in the FX root. That's the base for UA, or for the UAFX. But I can add it in dynamically to just an instance if I want. Again, this is if a model has some of the DI aspects in it, but I don't want to actually update the existing types in the model, I can just do it in a standard way, define it in the spec, how you add it to the instances. So it's you can have this, write this up in a standalone document even as an addendum to the existing spec. Right. I could also, I have my model now, this time it doesn't have DI in it, right? So there's nothing that I want to reuse in it. I may want to add FX to it. And I am going to update the spec, but I want to add it so that it's optional, whether you want to include it or not. So I can use the concept of add-ins. This is something else that's in OPC UA-based specs. I can define an add the functional entity and the assets in as add-ins. So they're an instance of an object in the companion spec. They can be optionally included, but if I include them in via profile or such that I list that, hey, I want to support FX, then they have to be there. I create an instance of the FX root and point to the newly created types below if they're present. So again, I can include a model using some base UA concepts very simply, very easily. The key point here is that has add-in reference is the only change you'd make to the existing companion spec, really. Right, so only model addition is an optional set of references. This is simple and addition to existing model. Profiles allow it. It's a very loose integration, but it can work well if there's no DI components already in the model. So another one is that if I have no DI in my model, I could just create a parallel model, right? So I can build this is sort of the end user case. I want to deploy FX in a controller that already has a bunch of other information. I can create an instance of the UAFX and use the organized references to point to the data that's in my existing model. Some of the examples I showed you guys on Monday, or on the first day I should say, illustrated a Raspberry Pi example. That made use of some of these things where I just create a parallel model and I'm talking to something that's existing. Again, this is no DI, no specifications updated. It's just a parallel model. Very easy to do for anybody, right? So let's talk a little bit about summaries. There's multiple ways of including the UAFX in a companion standard. All of these are the key points you sort of have to consider is it an existing published standard? Is it well adopted? Do I want to make changes to it? What sort of changes do I want, right? Would changes cause problems? Was it originally a DI, device integration spec-based model? Do you want it UAFX and required in all future versions of the model, or is it just something that's optional? How fixed do you want the mapping to? Do you want fixed inputs and outputs and a very fixed set of information? There's a lot of options. They can be mixed. So if I want an asset model, maybe they had DI or had some of the DI components in it. So I make the asset model an interface and add it. But the functional entity will be an add-in since it's very different. You can mix the two. The only things that are required is you do need that FX root in an automation component instance in what you end up building that provide sort of the hooks and the pieces needed for having it all working, right? I didn't discuss the connection manager in here because the connection manager is designed to be standalone. We required it in profiles, but all along it's been written up so that you can have it implemented in its own controller, just standalone. So the implementation of the connection manager and the addition of a connection manager is just a standalone piece. It doesn't have to integrate into any companion spec. It's just a facet that you have to implement for the current controller profile. In the future, there'll probably be profiles that don't require connection managers, depending on what you're doing. But for this initial case of controllers, you know, it's included. That's pretty much brings me to the end of my presentation. I believe that I'll turn it back to Peter at this point.
Thank you both, Paul and Greg, for your presentations. And now this immediately leads to the next presentation, because after you have been implementing your controller according to the UAFX profile document, part 84, and after maybe adding the one or the other companion model on top, you now want to make sure, and your customers want to make sure, that what you implemented is compliant to the published specification, to not run into any interoperability issues. And this is now the right time to hand over to Thomas Schreck, who will explain to us how certification and conformance testing is currently being planned and developed for UAFX. Thomas, please go ahead.
Hello, my name is Thomas Schreck and I'm Senior Test Engineer at the Schneider Electric Interoperability Test Lab. I'm chairing the FLC Test Development Workgroup, which is responsible to develop the test case descriptions for the OPC UA field exchange specifications. Today I want to present the certification and conformance activities regarding OPC UA field exchange, also called UAFX. I will start with an overview of the current OPC certification process and will then continue with the extensions to cover the requirements of UAFX. I will conclude with the FLC test development workflow and the timeline for UAFX conformance testing. Starting point of the UAFX certification and conformance activities was the OPC certification process. The OPC certification process is illustrated on this slide in a simplified version. The OPC certification program is controlled by OPC compliance. The responsibilities of OPC compliance are the accreditation of OPC labs, the assignment of products to OPC test labs, and issue certificates for products that passed successful testing in an OPC lab. First step in OPC certification is conformance testing, followed by interoperability, robustness, and usability testing. Last step is efficiency testing that verifies that a product operates stable in a loaded condition for 72 hours. OPC UAFX is a set of concepts and standards extending OPC UA with mechanisms required by industrial communication networks down to the field level. The OPC UAFX certification program was targeted to leverage the OPC certification program when possible. Existing processes are reused during the development and later for running certification of UAFX products. The FLC test development workgroup used the existing templates to create test case descriptions. These test case descriptions will be shared in the OPC UA profile reporting tool when the UAFX certification program is launched. UAFX products will follow the existing OPC certification process, extended to cover UAFX requirements to get certified. The well-known UA-CTT will be used for UAFX conformance testing. We selected existing OPC UA test cases and created new descriptions and scripts if necessary. The majority of UAFX testing will be automated, and only testing of functionality that doesn't allow more automation needs to be executed manually. FLC-specific requirements, like mandated certification to sell UAFX products, are added to the OPC certification program. Also, certification capabilities for field-level specific technical features like deterministic Ethernet, single-pay Ethernet, and functional safety needs to be integrated in the OPC certification program. This slide illustrates the extended OPC certification process for UAFX. The majority of UAFX test cases currently developed in the FLC test development workgroup will become part of compliance, interoperability, and robustness testing. The TSN Industrial Conformance Collaboration, short TIAC, was founded to develop test procedures for the IEC IEEE 6802 standard. OPC is active part of this collaboration and will integrate conformance testing for 6802 in the OPC certification program as soon as test procedures are available. OPC Compliance is working on adding capabilities for Ethernet APL testing to the OPC labs. All SDOs involved in Ethernet APL agreed on accepting each other's testing results. That means OPC compliance will not require retesting of APL technology when the product was already conformance tested by another SDO. For any safety product, certification by an authorized body is mandated. Precondition for safety certification is that the product passed OPC certification. The OPC UA compliance test tool offers automated testing of OPC UA products for compliance to the specification. Conformance testing with the UA-CTT covers several aspects. First aspect is a validation of the implementation of base OPC UA functionality. Base functionalities are, for example, service sets like attribute read, attribute write, subscriptions and monitored items, method calls or sessions. Security features like certificate validation or support of certain security policies are also base functionalities. Second aspect is the verification of the information model. The CTT is checking that objects, object types or data types and their instances match the definitions in the specification. Verifying that access to restricted nodes is limited to authorized users belongs also to the information model verification. The CTT verifies that operations triggered by service requests deliver the expected result, and that the product meets the performance and capabilities claimed by the product specification. The majority of UAFX conformance testing will be executed automatically with the help of the CTT. We create testing for the UAFX information model verification of automation component, asset model, and functional entities objects. We create extensive testing capabilities for the connection establishment validation. We are calling the connection establishment method or the underlying methods like create connection endpoint, establish control, verify function entity or verify asset, and evaluate the service responses and the operations triggered by the request. Offline engineering and network performance validation will also be covered by conformance testing. The FLC Test Development Workgroup is responsible for the definition of test procedures for validating functionality defined in the UAFX specifications. The first step in the FLC test development workflow is the grouping of functionalities defined in UAFX specifications into conformance units. Conformance units are defined by the architecture and other technical workgroups responsible for writing specifications. The conformance units are forwarded to the test development workgroup, which develops test case descriptions based on the specifications for every conformance unit. The complexity and number of test cases depends on the conformance unit. For some conformance units, only a single test case is sufficient, whereas other conformance units require 30 or more test cases. The test procedures are forwarded to the OPC compliance workgroup, which creates the test scripts that are then integrated into the CTT. The FLC prototyping workgroup develops prototypes for features defined in the UAFX specifications. The prototypes are used to validate the CTT extensions created by the compliance workgroup. The results of the test run against the prototypes are investigated to ensure reliable conformance testing for UAFX products. I want to close with a quick timeline of the UAFX certification conformance activities. The FLC certification requirements workgroup is responsible for extending the OPC certification program to cover requirements of field-level communication. This group was kicked off in August 2019. The certification requirement workgroup recommended the founding of the test development workgroup to the steering committee. The steering committee followed the recommendation and the test development workgroup started in October 2020. This group is composed of validation experts from various fields in industrial communication. We used the time when no stable specification was available to become familiar with OPC UA conformance testing by the help of OPC compliance. When RC1 of Part 81 was released in March 2021, the specification was stable to start with test case development. Since July, is the first beta version of the UAFX CTT available for internal validation against UAFX prototypes. Part 84 will be released in October 2022. First UAFX products are expected 6 months after release of the specification. The extended OPC certification program for UAFX controllers needs to be available until April 2023. That was my presentation on the UAFX certification and conformance activities. Thank you for listening.
Thank you very much, Thomas, for the really good overview about how we are creating the enhancements to the testing tool and how we will ensure cross-vendor interoperability. Thank you. We are now coming to the final presentation of our digital event. Before we then start the Q&A session for day 3, and I'd like to talk in the following about the next steps and the outlook to the future. Now, as you have already heard several times over the 3 days, we are currently having the 5 specification parts 80 to 84, in the final member review. So these release candidates that have been submitted for OPC Foundation member review will then become the first public released UAFX specifications. To explain a little bit more about the concrete status, you see here that we started back in April 2021 with a completed first release candidate. At that time, we recognized it's too early for sending this out for member review, so we immediately started the release candidate 2 for the parts 80 to 83. We finalized this RC2 end of November last year and started then the member review, which is 60 days member review, and then an additional 30 days for the opt-out, which has to do with the IP policy of the OPC Foundation. The member review, including the opt-out, was finished then end of February, and we still found some content that needs to be improved. At the same time, the prototyping also had not sufficient progress. So that's why we started on release candidate 3 for parts 80 to 83, that we then finished end of May. We started the member review for these 4 parts beginning of June, and our member review plus the opt-out will be finished end of August. In parallel to completing parts 80 to 83, we started to work on the controller profile, as you have heard before from Greg. So this part 84 was finished approximately 4 weeks after completing parts 80 to 83. It's clear that this comes a little later because it's referencing the parts 80 to 83, and in addition, certainly it references other parts of OPC UA, and also has external references to standards, for example, out of IEEE. Now this part 84 was completed end of June. We started the member review for this part 84 beginning of July, and this is finishing, including the opt-out, end of September, maybe very early in October. Now we're still continuing the prototyping, and the goal is to have sufficient progress with the prototyping when we finalize the member review of part 84, so that we are then able to put together a complete package of all the 5 parts of UAFX and then go public with this final released specification. So we expect Q3 of 2022. This gives us another 4 weeks after member review, including opt-out, has been completed. So I think end of October, sorry, is a realistic publication date. I want to emphasize that all of you that don't want to wait until this is public, and in case you are not already OPC Foundation member, think about a membership. You have then early access to the release candidates, and if you sign up for the working groups, you even have access to all the early drafts and also the later drafts, certainly. Okay, so let me continue. Now, as mentioned in my introductional speech, the focus on this UAFX specification is controller to controller. And because we now completed work, just need to wait for additional comments out of member review, we have planned the kickoff meeting for the next project phase. This is what I typically call it. And this is then extending existing concepts for controller to device, C2D, including device to device, D2D. The kickoff will be held on July 26 to 28, so 3 days at Schneider Electric in Andover, close to Boston in the US. And as you have heard, all the working groups are open to all the OPC Foundation members. All OPC Foundation members are invited to participate. At the moment we have, I believe, 50 to 55 registrants for this, so it will be a big kickoff where we then plan the detailed content, where we hand over requirements that have been elaborated. So this is a really important milestone for us. All right, so what can be now expected? What are we dealing with in the next project phase? Certainly we keep the overall solution approach with the layered stack approach, as we have mentioned several times. So we are building upon what is already there with OPC UA and the existing concepts and models of UAFX. Certainly we will enhance the existing concept for additional requirements for the field devices and for the connectivity between controllers and field devices. So this has then to do with the extensions to the automation components, whether it's information modeling or some enhancements to the connectivity or to offline engineering. We then concentrate on the specific models. I typically call them device type specific models. So we will work on an I/O facet covering all the various I/O types, as there is a broad range of different types like compact I/Os, modular I/Os, I/Os with subbuses. So this will be one important element. We continue work that we already started. I come to this in a second, on motion to cover different motion devices. Details follow on the next slide. And we start a new working group working on field instruments, or typically also called process instruments. So this is then additional facets to the base facets that we have for the various field devices. Certainly, networking plays an important role. For field devices, certainly the advanced physical layer as an underlying physical layer is highly relevant, but also for some of the use cases in the connectivity between controllers and field devices, such as motion control. certainly also deterministic Ethernet, and then enhancements to what you already have heard about with Ethernet TSN is important. Now, to give you a little bit more details on the motion related activities, it's not that we start from scratch, as we already launched our working group on motion back in June 2020. At that time, we already had requirements approved by the steering committee of our FLC steering committee. So the working group started, although it had no relevance now for the first UAFX specification release, as the focus is there on controller to controller. Work is based with regard to motion on ZIP Motion and Sarcos. There is an agreement with the ODVA and Sarcos International. As mentioned on the first day, we have no intention to reinvent the wheel, but to rely on proven concepts. This is the approach we took here. And the first specification that we are currently working on are dealing with servo drives, frequency converters, and you find some additional specific devices that we cover here in this list. I'm not going into details here now, but the important message is we are not starting now from scratch a new solution. We're extending what we already elaborated for UAFX and continue work that we already started, like for example on motion. We might adapt a little bit our working group structure for the next project phase. Here you see the existing working group structure with all the working groups that are in place at the moment. So we expect that certainly there will be a working group dealing with the I/O facet, with the models for the I/O types. Possibly we merge this with also existing working groups. So this will be discussed in the kickoff meeting. And certainly there will be a new working group dealing with the instrumentation facet, as you have seen on the previous slide. But in principle, the structure will remain the same, and we will continue with the working groups working on safety, working on motion, prototyping, test development, and all the working groups working on the base concepts. For your information, I have here a list of all the existing working groups in place, also with the working group chairs. So you have an overview who is involved, who is in the responsibility for the various activities. And you find also later a link on the homepage where you also find the email addresses in case you want to get in direct contact to the one or the other. Okay, now even I explained this slide already on day one. I think it's an important slide when we now talk about the next steps and the outlook for UAFX. You see here the today's situation with controllers communicating OPC UA up to the edge, to the cloud. OPC UA is used for use cases like monitoring, diagnosis, historian, data access. Controllers are still using the different field buses or real-time Ethernet solutions to communicate with the field devices. And certainly what is also available today already is having OPC UA as a so-called second channel to communicate over these field buses or real-time Ethernet solutions to the various field devices. In this case, OPC UA is used for monitoring and diagnosis. This is the second channel. And so to say, the first channel is the channel to control the field devices, to exchange the process data, and this is done then with the first channel, and this is then one of several connectivity solutions in the market. OPC UA here is a homogeneous communication interface, so it's not depending on the field bus A or field bus B. Now with our first specification release, UAFX, we are now harmonizing in the first step the controller to controller communication. Here we use OPC UA for control. As you have heard over the 3 days, we are using UAFX connections to exchange process data with different options for the underlying networks, including deterministic transport. And as you have heard today, also combined with OPC UA safety for functional safe communication across these controllers. And now with the next project phase that we are now starting, we are extending the concepts to bring OPC UA down to the field devices, and this is then OPC UA as a so-called first channel. No need for a second channel because this is OPC UA, and in this case we are now using OPC UA for all the different purposes, control, monitoring and diagnosis, and we establish OPC UA as one consistent homogeneous communication solution and interoperability solution, vertically scaling from field to cloud, but also horizontally. And the important message is, like Stefan mentioned on the first day, supported by all the major automation suppliers in the world. And that means it's becoming the standard of the future. Okay, let me quickly give you some details on different upcoming exhibitions where we have dedicated demonstrations on UAFX. So we will show these multi-vendor demos we have been talking about, also a demonstration of OPC UA safety and the 5G communication part. So we will be at the Achema show in August, where we have one of the biggest booths OPC Foundation ever had. We will be at the IMTS show in the US, also a few weeks later at the PEG Expo in the US, and then the SBS show in Nuremberg, Germany, beginning of November. Certainly OPC Foundation is present in many other events, but if you want to have a look at the demos, you want to find out detailed additional information on that, these are the major shows where you will have the experts for UAFX present. Now, before I come to the final slide, let me take the opportunity here to remind everyone that we will provide the links to slide decks, recordings and Q&A compilations a few days after the event, and we will also provide a link to the testimonials that you have seen before we started the sessions every day. We selected always 5 testimonials before starting the webinar, and you will then receive a link to the complete compilation of 15 testimonials. Might be interesting to listen again what these representatives had to say and what they feel is so beneficial for the industry and for their customers. All right, with that, I'm at the end of my presentation of talking about next steps and outlook. You find here my contact details. You find some links where you find additional information. We have also some white papers and brochures that help you to, let's say, get a good understanding of what UAFX in combination with other standards is about. All right. Thank you very much for your attention.